Welcome to Fuzzy Mathematics, the basics. In the previous lectures, we have talked about the properties of the algebraic structure, the fuzzy polar set, together with the two binary operations, the union and the intersection, and one unary operation, the complementation, which plays an important role in fuzzy mathematics. In this lecture, we will change the subject. We are going to talk about the generalized union and generalized intersection of fuzzy sets. The union and intersection of fuzzy sets we have talked about is based on the maximum and minimum operations of real numbers in the closed interval from 0 to 1. This pair of operators, usually called Jolly operators, is the most widely used pair of operators in fuzzy theory. Here, the degree of membership of X in the intersection of A and B is determined by the smaller one of the two degrees of membership. That is, the larger one will have no reflection on the result, no matter how large it is. But if we choose a different operator, it may have certain reflection on the result. Different operators are proposed in the definitions of different generalized unions and generalized intersections. These binary operators on the closed interval from 0 to 1 are collectively called fuzzy operators. An operator similar to the maximum operation is temporally called generalized maximum. The operator similar to the minimum operation is temporally called generalized minimum. I'd like to mention that we will not give the definitions of generalized maximum, generalized minimum, and fuzzy operators at the very beginning of this lecture. We are going to find out what kind of properties a generalized maximum should have, what kind of properties a generalized minimum should have, and what kind of properties a fuzzy operator should have. That's what we are going to do in this lecture. Let's begin. Let A and B be two fuzzy sets. The generalized union of A and B of X should be equal to the generalized maximum of A of X and B of X. The generalized intersection of A and B of X should be equal to the generalized minimum of A of X and B of X. We use these notations to denote the generalized union and generalized intersection. We use these notations to denote the generalized maximum and generalized minimum. The properties of generalized union and generalized intersection totally depend on the properties of generalized maximum and generalized minimum. So these fuzzy operators, these binary operations on the closed interval from 0 to 1 must be rational, such that the corresponding generalized unions and generalized intersections are rational. We try to find out what kind of binary operators on the closed interval from 0 to 1 are rational. First, let's find out what kind of properties the generalized union and generalized intersection should have. Naturally, they should satisfy the following properties. Firstly, the commutative laws. The generalized union of A and B should be the same as the generalized union of B and A. The generalized intersection of A and B should be the same as the generalized intersection of B and A. Secondly, associative laws. The generalized union of A and B union C should be the same as A unions the generalized union of B and C. The generalized intersection of A and B intersects C should be the same as A intersects the generalized intersection of B and C. Thirdly, monotonicity. If A1 is a subset of A2, B1 is a subset of B2, then the generalized union of A1 and B1 should be a subset of the generalized union of A2 and B2, and the generalized intersection of A1 and B1 should be a subset of the generalized intersection of A2 and B2. In addition, they should satisfy the following boundary conditions. The generalized union of A and the universal set should be the universal set. The generalized union of A and the empty set should be A. The generalized intersection of A and the universal set should be A. The generalized intersection of A and the empty set should be the empty set. Actually, the boundary conditions are the domination laws and the identity laws. We found that the generalized union and the generalized intersection should satisfy the commutative laws, the associative laws, monotonicity, and boundary condition. What does that mean? Let's use the commutative laws as an example. First, let's take a look at the first equality of the commutative laws. If the generalized union of A and B is the same as the generalized union of B and A, then the generalized union of A and B of X is the same as the generalized union of B and A of X for all X. In other words, the generalized maximum of A of X and B of X is the same as the generalized maximum of B of X and A of X for all X. Next, let's take a look at the second equality of the commutative laws. If the generalized intersection of A and B is the same as the generalized intersection of B and A, then the generalized intersection of A and B of X is the same as the generalized intersection of B and A of X for all X. In other words, the generalized minimum of A of X and B of X is the same as the generalized minimum of B of X and A of X for all X. What does that mean? That means if the commutative laws hold in this algebraic structure, then the commutative laws should hold in this algebraic structure. Similarly, we can find that if the associative laws hold in this algebraic structure, then the associative laws should hold in this algebraic structure. If this algebraic structure has monotonicity, then this algebraic structure should have monotonicity. As to the boundary conditions, let's check them one by one. If the generalized union of A and the universal set is the same as the universal set, then the generalized union of A and the universal set of X is the same as X of element X. In other words, the generalized maximum of A of X and X of element X is the same as 1. That is, the generalized maximum of A of X and 1 is the same as 1. Next, if the generalized union of A and the empty set equals A, then the generalized union of A and the empty set of X equals A of X. In other words, the generalized maximum of A of X and the empty set of X equals A of X. That is, the generalized maximum of A of X and 0 equals A of X. Next, if the generalized intersection of A and the universal set is the same as A, then the generalized intersection of A and the universal set of element X is the same as A of x. In other words, the generalized minimum of A of x and the universal set of x is the same as A of x. That is, the generalized minimum of A of x and 1 is the same as A of x. Next, if the generalized intersection of A and the empty set is the same as the empty set, then the generalized intersection of A and the empty set of x is the same as the empty set of x. In other words, the generalized minimum of A of x and the empty set of x is the same as 0. That is, the generalized minimum of A of x and 0 is the same as 0. All these A of x are real numbers in the closed interval from 0 to 1. What does that mean? That means if this algebraic structure has the boundary conditions, then this algebraic structure should have the corresponding boundary conditions. To sum up, the algebraic structure should satisfy the following properties: the commutative laws, the associative laws, monotonicity, and the boundary conditions. If A1 is less than or equal to A2, B1 is less than or equal to B2, then the generalized maximum of A1 and B1 is less than or equal to the generalized maximum of A2 and B2, and the generalized minimum of A1 and B1 is less than or equal to the generalized minimum of A2 and B2. Boundary conditions: the generalized maximum of A and 1 should be 1. The generalized maximum of A and 0 should be A. The generalized minimum of A and 1 should be A. The generalized minimum of A and 0 should be 0. Both of the two operations should have commutativity, associativity, and monotonicity. What's the difference? The difference is the boundary conditions. Nevertheless, the boundary conditions still have something in common. The generalized maximum of 1 and 1 is 1. The generalized maximum of 0 and 0 is 0. The generalized minimum of 1 and 1 is 1. The generalized minimum of 0 and 0 is 0. Now we have made enough preparations for the definition of fuzzy operator. A fuzzy operator is a function on the closed interval from 0 to 1 that satisfies the commutative laws, associative laws, monotonicity, and the boundary conditions. The ordered pair 0, 0 is assigned 0. The ordered pair 1, 1 is assigned 1. The definition of fuzzy operator is a composite of generalized maximum and generalized minimum. Obviously, we need more specific definitions for each of them. The generalized maximum is commonly called triangular norm. A function t is called a triangular norm if it has commutativity, associativity, monotonicity, and t of A, 1 is the same as A. A triangular norm is usually called T-norm. The boundary condition of T-norm is t of A, 1 is the same as A. Next, the generalized maximum, which is usually called triangular conorm. A function S is called triangular conorm if it has commutativity, associativity, monotonicity, and S of A, 0 is the same as A. A triangular conorm is usually called T-conorm or S-norm. The boundary condition of S-norm is S of A, 0 is the same as A. All the three kinds of operations have commutativity, associativity, and monotonicity. What's the difference? the boundary conditions. The boundary condition of T norm is T of A, 1 is the same as A. The boundary condition of S norm is S of A, 0 is the same as A. That's the end of this lecture. Next time, we will continue this topic. Thank you.